Now we will have a self-employed man, founder of a one-person company who has made and who is making fully open source chips down to the silicon. Welcome, Daniel Schultz.
Hello everyone, and thank you for this very kind introduction. My name is Daniel, and I'm going to talk about how to make fully open source chips. Before we dive into the ASIC flow, I will briefly introduce ElemRV, and I will talk about the open source tapeouts I made. So ElemRV is a collection of end-to-end open source RISC-V microcontrollers. End-to-end in this context means they are open source from design files to produced silicon. It contains multiple platforms based on element names. So the ElemRV is just a combination of elements and RISC-V. It's fully written in Spinal HDL, licensed under the CERN Open Hardware Language W2.0, and implements an FPGA and an ASIC workflow. The history of ElemRV is also tightly coupled to the IHP, and you will hear me talk a lot about the IHP. It's the Innovations for High Performance Microelectronics. It's a publicly funded research institute that's focused on silicon germanium transistor electronics. They operate a very small pilot line at their facility to produce their research technology on these silicon germanium bipolar transistors, and they are located in Frankfurt Oder, that's at the border to Poland in Germany. They had two key fundings some years ago. First, they got funded in 130 nanometer open source PDK. Secondly, they got funded free MPW runs to validate those analog and digital components made with this open PDK. Alright, so analog designs are in IHP's wheelhouse, and they had a lot of analog designs, but they lacked digital designs. I had a RISC-V microcontroller on FPGAs, and I wrote an hyperbus interface to connect external memory. So they asked me if I want to tape out my microcontroller with their open source PDK. And you can see on this image, this is the first tape out done with the open source PDK. The design philosophy was very conservative. The PDK was in alpha stage, so the main goal was to get a bootable silicon. As you can see, this silicon is not really dense. It's also a flat design, so it was very conservative. I received the silicon bags in February last year. I found one bug in the hyperbus interface, which is unable to run data and instructions at the same time in the external memory. The RISC-V core is working, all included interfaces are working, and beside that one bug, it's actually the first booting silicon with the IHP Open PDK. Since IHP is the only foundry in Europe with an open source PDK, it's technically also the first European end-to-end RISC-V microcontroller. The best part about this entire tape-out is I did this at home on my private PC, and I did not sign any NDA to get silicon back on my desk. Alright, and since there were still free MPW runs available, I did another tape out last year. I fixed the hyperbus interface. It's now running Sapphire RTOS. I added an on-chip RAM. It got more IOs. It got also more interfaces to silicon-proof them, and it now has a mask IES included, because there's a research team in Germany that will try to run side channel attacks on this chip, since they have the layout files. Alright, so that's about the tape outs I made. Let's talk about the open source ASIC flow. This is a very simplified overview. What we need is we need RTL, we need design files, we need a C ring, we need one bond pad. Then we're going to use OpenRoad to generate a GDS2 file, a 2D layout file. We're going to add metal dummy fill, and then at the end we run design rule checks. Okay, so the RTL EDA tools are commercial or open source, doesn't matter. They only understand, normally it's just Verilog. ElemRV is fully written in Spinal HDL, so you cannot feed directly the ElemRV code into the EDA tools. However, Spinal HDL is a Scala-based framework to actually generate Verilog and or VHDL. The big advantage about using a high-level language like Spinal HDL is you have modern programming constructs. You have it's using Scala. It's Scala-based, which means you have the Java infrastructure in the background, and you can do simple things like file.io to read from or write to files, for example, which is impossible with Verilog. Okay, but in the end, it doesn't matter what you use. If you use Spinal HDL, Chisel, or just plain Verilog, you need your design defined in Verilog. Okay, so next we need a C-ring. Some foundries actually call it a SCART ring, which is a ring around the entire chip using all metal layers. It has multiple purposes during the lifetime. So first, during manufacturing, it's blocking ionic contamination from the wafer. Then when separating dies from the wafer, it's reducing mechanical stress. It's also stopping cracks from going from the edges into the chip. And then during runtime, it's preventing of getting moisture into the chip. And this image is the IHP C-ring. So you can see this is a cut through of the C-ring. You can see on the lowest level the green layer is the active layer. Then IHP is using 5 normal metal layers, and then it has 2 thicker top metal layers, and in between are vias. Alright, so next we need a bond pad or bond pads, which is bond pads are basically exposing metal area on the highest layer to connect the chip to the outside world. They are normally placed on the outside of the I/O cells, but on the inside of the C-ring. They can vary in sizes, but typically they are something like 50 to 100 micrometer. They can have different shapes. IHP is providing square, octagonal, and circular shapes. And there are also different bonding techniques. For example, there is wedge bonding and ball bonding, which are both called wire bonding. So if you open a chip or if you X-ray them, you might see small wires. This is wire bonding. And then there's also very popular now, it's like flip chip, where you flip the chip around and then solder the chip bond pads directly onto a silicon or PCB interposer. And the bonding technique also defines the requirements to the size and the shape. And this is a 70 by 70 square micrometer square bond pad with the IHP PDK, and you can see this is a huge metal area on the top metal too, and then also on the lower normal metal layers. Okay, so we have our design files, we have a C-ring, a band pad. Now we can start actually laying out the chip. There are 2 popular open source ASIC flows right now. One is called LeapRoLane, and then there's OpenRoad flow scripts by the OpenRoad project, which is a makefile-based configuration. This is, for example, part of the ElemRV configuration. So you need a design name. This is ElemRV top, which is also the Verilog top module name. Then you need a nickname for logs and just for logs and for directories. Now we need to select a platform. This is IHP, but this could also be Sky 130 or Global Foundries 180. Then you define all your Verilog files. Now it's getting a little bit more interesting because we need to define a die area, and we also need to define the core area size. Next we define corners, because chips normally come with a temperature range. What we do here is we define a slow and fast timing library. For example, if you have a temperature rating like minus 40 to 110 plus degrees Celsius, then the slow timing library defines the highest temperature point, and the fast timing library defines the lowest temperature point. And an open road can actually use these informations during place and route to guarantee the chip will work in the entire temperature range. Okay, in the end, we also need to define an SDC file, which is the clock constraints, to define which input clocks we have, like do we have gate clocking, etc. Okay, so we start the RTL to GDS flow by actually synthesizing the RTL into a gate level netlist. For example, if you design in RISC-V, you will most likely write an ALU, and then you will use something like register 1 plus register 2. We assume registers are 32-bit wide. There is no standard cell available that implements this operation. It's a high-level operation in Verilog, and for example, USIS, which is used in Open Road, is transforming this operation into a network of standard cells to implement the same feature. Next, Open Road will lay out the die area, and then will also lay out the core area. It will place macros, could be, for example, RISC-V CPU or memory. And in the end, lastly, it will do the power distribution network. And this is the chip at this point. The black background is the die area. That is the area you pay for when you tape out the chip. Then you can see this chip has 20 bond pads. Next to the bond pads or inside is the I/O ring. And then it's light blue, pink is the power distribution network. This is a power and ground ring, and then there are power and ground strips on top. And in the inside, this is the actually core area where the logic will be located later. And on the lower left is a macro cell placed. Okay, so next we're going to do the place and route. So first we will start placing standard cells, then we will generate a clock tree. Next we will do the global routing, followed by a more detailed routing. And in the end, the EDA tool will extract the per-Citrix values from the entire traces of the network, and then we run timing closure. Those checks will most likely not pass in the first run, so we'll go back to the first step, and we'll reorganize standard cells, it will reorganize the clock tree, it will run the global and detailed routing again. And we'll do this over and over and over until there are no violations. And this is in this chip is now, you can see this very small cloud over the macro. That's where the standard cells and traces are located. This is obviously not a RISC-V microcontroller. This is a small example, but this is how this looks like. All right, now assume that no violations are in the place and router. The final step is to perform some antenna rule checks. So basically, the EDA tool is checking for any traces which are connected to transistors, and they could act as antenna during manufacturing, because that could potentially destroy the transistor. It will also do some more minor checks. It will also now place the C-ring on the outside and then export the GDS2 file. So we now have a GDS2 file, but we are not done. The problem is that we have a very undistributed metal density in each layer. And the problem is, if we do during production, they will do a chemical mechanical polishing, and that could cause in a different variation of thickness after polishing. And the problem is that could get unpredictable electrical characteristics. For example, in this image you can see top metal 2 has bond pads, has the I/O ring, and then there's only a little bit power and distribution network. So it's very undistributed. There's a lot in the I/O ring. There's almost no metal in the core area. And the solution is to add just metal dummy fill, basically. And you can see top metal 2 here in this case has very big shapes because there's a higher need to fill this layer. There are some layers not filled because there's probably some routing or some macro located, so there's no need. Alright, and the final step is running design rule checks. This is probably also the hardest step of all of them. The problem is that different foundries, they have different nodes and technologies, they have different tools, they have different experience, so they provide a unique rule deck for their process. And the other problem is that EDA tools, they don't check for all rules because some are just out of scope, and on the they are also optimized for speed. And this image you can see the design rule check for top metal 1 of the IHP process, which is also very simple, but there's one rule, that's the second one, it's called TM1.B. It's described as minimum top metal 1 space or notch, and the distance is 1.64 micrometer. And the problem is that if two metal 1 shapes are located closer to each other, closer than 1.64, there's a risk of getting shorts. So that's why it's important to keep those distances. And yeah, as I said, this is probably the hardest step because you do all these, you do your tape out, you run design rule check, and then it's like 2 days until the tape out deadline, and then you question your life. Alright, so that's very quick run through the ASIC flow. The key fundings for the IHP process PDK are now over, and IHP is providing open silicon MPW services. There are 1,500 euro per square millimeter for open source designs only. So they say this is their manufacturing cost basically. And they have 3 upcoming tape out dates this year. There's one in March. It's the CMOS only, so this is only standard digital standard cells, which is faster to produce. Then in July is the CMOS 5L, which is again only standard digital cells, but it's only 5 metal layers instead of 7. And in October is the G2. That's with the high speed bipolar transistors. Perfect for mixed and analog designs. And if you're interested, I think the minimum size is 1.8 square millimeters, so you can also start with very small designs for less money. And if you're interested, you can use this QR code to register. And if you don't trust my QR code, you can use this link below. I made all these images with Blender GDS. It's an add-on for Blender to directly import GDS2 files. Then you can use Blender Cycle render engine to generate high-quality 3D images. It's very nice for like presentations, if you are working on publications, posters, documentation. And of course, ElemRV is also open source. So if you're interested in using a RISC-V microcontroller FPGAs, if you're interested in taping out open source or open silicons, it's silicon proven on the IHP process. Yeah, I would also like to get feedback if there's something missing. That's basically it about open source chips. Thank you for listening, and feel free to connect. Do you have 1 more minute? Or do you have 1 minute? because this is World RISC-V days, I thought I'm actually putting a RISC-V core render one. So this is a VEX RISC-V CPU, 32-bit, 5-stage pipeline. It's written in binary HDL, and it has a 1 kilobyte S level 1 instruction and 1 kilobyte data cache. And as you can see, this is like 130 nanometer. SRAM is super expensive. Yeah, it's very big. And the other thing is, if you do open source chips, you can actually render your entire chips and make nice images. Yeah. Thank you.